Hey everyone, I'm excited to be here. This is my first P99 conference. I'm going to be talking about P99 published performance on a NATS IO system, which we'll talk about, but spread across multiple AZs and all three major cloud providers all at the same time. So we were asked to talk a little bit about something that's unique to us, something cool we've done. The thing probably most known for right these days is NATS, which we'll talk about a little bit in this talk. Also Cloud Foundry, which was a platform as a service offering from VMware. Kind of think of it like a Heroku for the enterprise. Um, I also did the Google Nginx APIs when I was at Google, Gmail Photos, and when I was at TIPCO, I co-founded the Rendezvous team and architected the modern version of that and architected TIPCO's EMS system. Um, Another thing about me is I actually conducted the federal trials for the first intra-arterial blood gas device when I was 22, 23 years old, out of Stanford and with a company that's no longer around called Puritan Bennett down in Carlsbad, California. And what I like to do when I'm not working, although I work almost all the time, is traveling and boating and playing golf sometimes. So what's our goal? What are we actually trying to achieve? Again, the setup is that we're looking for less than 20 millisecond P99 streaming guaranteed published times across all major cloud providers. And each cloud provider is going to have multi-redundancy across AZs. We're going to use NATS, and we'll talk a little bit about what that is in just a second. JetStream is our persistence layer there to publish the messages. And again, they'll be stored in a quorum across multiple clouds at the same time through consensus. And the requirement for this project was that they had to be in all three cloud providers, and they had to be HA and multi-AC in every cloud provider. And the P99 under load needed to be less than 20 milliseconds, and they were conversing over a 1 gigabit private link. So what is NATS IO? Well, NATS IO and JetStream, which is built in, that comes as a single binary server, is a system that can do microservices in RPC. It can do streaming. It can do key values, pub sub, and object stores. And the nice thing about NATS, at least in our opinion, is that it's a modern connective technology. Using pub sub underneath the covers gives us location independence, and we don't need things like load balancers or GSLBs or perimeter security models or VPCs or any of that. And so, as we said, it's a modern connected technology. It's built specifically for adaptive edge and modern distributed systems. It's based on a core pub sub engine. I've been doing these types of systems since the early 90s. But we also have, again, streaming, persistence, key value, and object stores as well. It provides at most once, at least once, and exactly once with an asterisk because everyone defines it differently. For those that know what I'm talking about. But again, it's packaged as a static binary. It's fairly small, about 14 or 15 meg, I believe. It can run on very, very big hardware. It can run on very, very small hardware, even like Raspberry Pi 02s. One of the other interesting things is that it has secure multi-tenancy. So we call it the Coke and Pepsi problem or the FedEx and UPS problem. And JetStreams are our persistence and clustering / consensus technology, which we'll talk a little bit about just to give a basis on what we were working with to kind of get to where we need to be. And there's more info if you want to check some things out. So the NATS topology within the system was, again, we had to have 3-node presence in every major cloud provider. Those 3 nodes had to be in different AZs, so they had to have HA components to them provided by the cloud provider. And they were interlinked between cloud providers with a 1 gigabit private link. And so the system in total was 9 servers, 3 servers per cloud provider, each individually stuck in its own AZ. And then all of those are actually put together in what we call a NATS cluster, which is a full mesh 1-hop. All have persistence through JetStream. All have opaque tags. The servers can be configured with tags that the servers don't know anything about, but things that are actually using the system and the infrastructure can actually use to do placement and anti-infinity, which we'll talk a little bit about. The anti-infinity tags, again, allow R3 streams across not only all 3 cloud providers, but again, as you're not just running one stream, you might be running lots and lots and lots of streams. they're actually spreading themselves out inside of the AZs as well. And there's DNS for each subsystem, cloud provider specific, and then the system as a whole. And so when we create a stream, and in NATS JetStream persistence technology, a stream is an ordered set of messages. And then we actually provide materialized views on top of that for key value and object stores and things like that. But creating a stream really, in this instance, is all about the anti-infinity tags, meaning we don't want to have to individually place peers in a stream. We just want to say, create a stream. And within the NAT system, you can say, I want to create a stream and I have some placement constraints. And you can be attracted to tags, servers that are having, running those tags. So I could say I want R1 stream on AWS, cloud AWS. Or I want one on, AZ number 2, cloud provider Azure. In this instance, what we mostly use is actually the anti-infinity tags. And so what that means is that we say, once you've selected a peer that matches a certain cloud provider, you can't pick it again. Within a cloud provider, once you've selected a certain AZ, you can't pick it again. And so on the presentation, you can see the little disks, essentially. So each one of those is a replica of a single stream. And so what applications see is they just publish a message and they get an acknowledgement back. And what's happening, which we'll describe here in a second, is going across this topology. And so to create a stream, again, we use the anti-infinity tags to properly place a replica of the stream in each cloud provider. What's nice, and again, goes back to that core pub sub, which most people might not know about. They're probably more familiar with microservices and streaming and key value stores and things like that. But a lot of those connective technologies are location dependent. You have to know who you're talking to, or you're talking to a load balancer, that then's doing something. And it's hard to have a load balancer at a global scale, so to speak. And so the neat thing about the way NATS works is that you can literally connect anywhere. Think of it kind of like your cell phone when it attaches to a cell tower. As long as you paid your bill and the cell tower is, can move traffic on your provider, that's all you need to know. And then the upper layers actually are essentially location independent at that point. NATS is the same way. So you can connect anywhere and say, I want to create a stream. The JetStream runs with what's called a meta layer. Think of it like DNA. So all of the system has a DNA of where things are supposed to be. And HA and R3 assets, they run a consensus algorithm that we adopted based on the Raft paper, but we layered it and built it on top of NATS. So NATS is actually the transport. So for JetStream running inside of a NATS server. And we did a couple things. We also added in fast cooperative transfer, meaning if I know I'm going down and I can't be the leader anymore, I can pass the baton very quickly. And then storage fault detection. So we use a very fast highway hash in and out all the time to disk from our friends at Minio. Once the leader is selected inside of the NAT system, inside of a NAT server, it actually creates a subscription, which again, that interest graph populates across any NATS topology whatsoever. And so any application can connect anywhere, send a message, and it'll make its way to the leader of the stream, which then runs the consensus algorithm. Once that's actually done, sends back the acknowledgement. And so, publishing to a stream, connect any server, publish anywhere to a subject that is what the stream is interested in. And in NATS, you can have wildcards, but in JetStream, you can actually have as many subjects as you want attached to a stream. You can even have other streams attached to a stream, and we can talk about that a little later. And again, an ACK is only sent once consensus has reached. And so in this situation, consensus is being reached between multiple cloud providers across the 1 gigabit private link. And so again, our goal was with this topology, with the setup, with NATS and NATS JetStream, applications that were connected anywhere in the topology had to be able to achieve a goal of less than 20 millisecond P99 streaming publish performance. So how do we do? So we've been engaged with this customer. They're wonderful. We really do enjoy working with them, especially on some of these goals. But when we started out, the system started not too heavily loaded, and the P50 and P75s were decent. But then as we started increasing the load, more streams, again, remember I said, think about it if it's not one stream, but there's lots of streams all spread out, more publishers, more consumers. The P50 still was kind of okay, but the P75 started to drift, and the P99 was Not good. Not good at all. And as you can see on the graph here, we've got spikes on some of these that are, north of 5 seconds. Some are almost up to like 8 or 10 seconds in some instances. And so we needed to figure out what was going on, and we knew this was going to be processed with this customer of ours. And they're out of Europe and in Fin services now. There's a lot of regulatory pieces that say you have to be multi-cloud. You can't just be in one cloud provider and provide these types of services. And so we needed to dig in, and we did. And so the NAT servers that are 2.9 or less, which is what was run in this one, by the time this airs, I think 2.10 is probably going to be out. They only have one connection between them. Now, NATS is completely asynchronous, meaning there's no such thing similar to HTTP where you put something in and something comes back. And of course, with HTTP 1.1, we introduced pipelining. Of course, HTTP 2 and 3 kind of get around that by multi-streaming. But NATS is a single stream, but everything is asynchronous. So response can come back whenever it wants to or not. But all traffic from multiple accounts, remember, NATS is securely multi-tenant. And by default, if you're in one account, you can't see anything from another account, and vice versa. They're all muxed across that connection. And so when a NAT server is running JetStream, JetStream itself has lots of internal subscriptions. So JetStream is actually not really that special inside, believe it or not. It's just using NAT's core publish subscriptions and things like that. It's layering on the at least once and exactly once and other features of JetStream. But of course, many of these are running online. So again, picture the diagram that we were looking at, and lots of publishers all kind of going at once. They might not be connected to the server that is housing the stream leader that they're actually publishing a message that's destined for. And so you can start to imagine, messages flying kind of all around. But again, every time a message is going between any two servers in a 2.9x or below system, it's all muxed over one connection between two servers. And so a lot of those would be running in line. Disk I/O. Now we punch through the kernel. We make sure that we actually do that. And we can actually do syncs. That's an option. You can configure that up and down. But by default, we do punch through the kernel, but once we have consensus, we return. And so we started to realize that disk I/O was kind of creeping into some of these inlines. And so as soon as an I/O might hiccup, if the message was coming across the route and was trying to actually do any type of I/O, disk in this case, it would start backing everyone up, obviously. Network I/O is actually already kind of offloaded, just the way the NATS server architecture is built. There's an execution context for every connection, routes, clients, gateways, leaf nodes, all that kind of stuff. And then when they're trying to switch, so NATS core, the original NATS server, think of it like a very high-speed intelligent switch. It actually can queue something up with very little contention. We had more than I wanted to, though, as you'll see in a second. And then it actually kind of taps the other execution context to say, you have something to flush out to your clients. And so we wanted to remove I/O from the hot path. And this is not, rocket science. It was something we should have done, and we just kind of overlooked as we were moving fast and trying to break things, so to speak. But we did the work to make sure that no I/O paths inbound from a route we're going to be blocked up by any type of I/O buckling. Now, as you notice, I said routes, and it's actually routes and gateways and some other stuff because they're all what we call muxed. A client connection is bound to one account only. And if you're trying to send a message that's trying to be stored, part of the cost of sending that message could account for that. But we actually already offload a lot of that stuff with the client as well. So we moved to a lock and copy. So we grab something on the wire. We realize that the subscription, which is an internal callback inside of the NAT server, they're flavored, and it kind of says, hey, you're going to do I/O. And it says, oh, well, if you're going to do I/O, we'll just copy the inbound raw message and allow route processing to continue. And so they're queued up internally for another execution context. And so we saw improvements for sure. P50 to P90 were looking pretty decent. But under load, when we really started pushing, we're still not getting great results, right, for the P95 and above, P99 especially, which was our main goal. And so as you can see, we're doing a lot better. You don't see any seconds anymore, so to speak, on the graph. But you do see pops up to 140 milliseconds, almost 200 milliseconds, I think, on the P99 on per cloud provider metrics. And so we still had some work to do. We had a lot of improvement. Obviously, disk I/O is going to be a big one. And again, shame on us that we even had that there. I'm happy to talk about, the failures as much as the successes. And this actually, I think, turned out to be a success for sure. Um, but we still had work to do, right? We still had more to go. And obviously, these things weren't even flattening yet, right? So you could tell there were some edge conditions that were hitting that were kind of impacting our results. And so we had to dig back in and we had to kind of figure out where things were happening, where they were going off the rails. And so we determined that we had some coarse grained locks. Now, what's interesting about locks is I think they've gotten so much better. And then, of course, when Sector and Meltdown and all the side cache type of things happened, things started kind of slowing down a little bit. But in the 90s, actually, coarse grain locks were actually way better than lots of fine grain locks. But we had a couple coarse grain locks there that were starting to experience contention under load. Lots and lots of publishers, lots of consumers, lots of streams. So think of a busy financial day, things just flying all over the place. The other thing is the customer was originally using interest-based retention streams. Now, NAT streams have a lot of different configuration parameters. At the application layer, usually you just kind of say, I want a p-value, I want, a stream or something like that. But in the server, there's a lot of options. And one is to be interest-based. So we have work queue, interest-based, limits-based. And interest-based says when everyone is finished with a message, you can remove it. And when you run an NRG group, every once in a while, the stream group is actually snapshotting the whole state of the stream, sans the data, that it can send over to the other side so they can compress the RAF log, compact it. And when we send it, it's pretty easy to say the first sequence is this, the last sequence is this. This is how many messages you have. This is how many bytes you have. But what we also needed to provide was which messages were missing. And again, this was in the original design where it was looking more like streaming and KB would be probably very lightweight. And we were that, but originally the state simply stored them as a slice of UNT64s. And that was a bad initial design for what eventually happened, because as we released JetStream out into the wild, people did like the streaming aspect of it for sure, event and data streams and things like that. But people really, really liked the key value semantics and started using it in ways that we had never thought of. This essentially exacerbated my bad design because the interior delete state started getting bigger and bigger and bigger. So you can imagine I'm running as the leader and I'm going, okay, hey, I'm kind of getting a lot of stuff in the RAF log and I can compact all that stuff down. But when I do that, I have to replace it kind of with a roll-up snapshot, which is what this is. But that started taking longer and longer and longer because of these interior deletes. And so we went about obviously removing the coarse grain locks. That was not too hard. In some instances, we went to atomics. There's different performance characteristics. NATS is written in Go. There's different characteristics between mutexes versus read-write mutexes versus atomics. And so some of the things we actually went and used atomics. And remember when we said if it was coming inbound on the route and we were matching it to a subscription, and again, routes in the setup that the customer has, the 2.9, it's actually inbound, you have to affinitize to an account, and then within the account, you have to match all of the subscriptions that you want. And if it was an internal subscription and it was marked as this could do I/O, we would use either a internal queue or an atomic only at that point. And so each function that needed execution had its own dedicated IPQ. So they aren't sharing so that there's no contention there either on those. And for those that do know Go, and I've been a big Go fan since 0.52, I think, Go channels are still, even though they've gotten so much better since the early days, they're still a little too slow, right, for this section in the server. The other thing that we had the customer do is switch to limit retention. So limit retention, you can act the messages, but in NATS, one of the things in JetStream, which again is our persistent technology built inside, one of the things that we did is we separated the notion of stream state and consumer state. And so a stream can actually run and have a limits-based retention policy, meaning the only time it removes messages is if there's a max messages or max bytes or max age or something like that. But that doesn't mean that the consumers can't be acknowledging messages and they won't get them back after they've acknowledged them, that kind of stuff. Um, and so moving from interspace to limit space removed all of those interior deletes, right? Because even though the consumers were ACKing the messages, that would never trigger kind of an interior delete. We call it the Swiss cheese or the laggard problem. The laggard problem was we had someone at sequence 2, and then we had someone at sequence 1,000,000, and then that was it. So you had 2 messages in a stream, but I had to represent, and again, the initial design was not well done. It was me. It was my fault. It's my bad. I didn't foresee that being a big issue there. And so now we have to store, 1,000,000 UNT64s and then encode them and send them over the wire to get all of the replicas synced up. And so, again, the large key values, which, again, we were really fairly confident that the key value store functionality of what we had delivered would be used for more lighter weight configuration type stuff. The first video that the team put out, I think on day 2, someone already had like 20 million key value pairs in a stream. And so we knew that we had to fix this. It wasn't that we didn't know it. We just had to make sure how to fix it. So we did, and it's redesigning 210, about a 1600x speed up in time and a 50,000 speed up in space on the wire. But the customer, and for this, these runs are still running 2.9 right now. So we switched to limit spaced. So those third results, we saw more improvements. P50, P99 were looking really decent. Under load, though, we still were, we're getting so-so results at the P99. And believe it or not, and I'll show you the graph here in a second, we determined that the memory system started to becoming the bottleneck. And at least from my perspective, I don't know if I've really ever seen that. One of the things that drew me to Go way back when it was originally created by Rob Pike was the fact that not everything went on the heap. It had real stacks. And so for those that know the difference, right, stacks are kind of free and heap is not. And so you could put things on the stacks. And back in the old TIPCO days, I spent a lot of time designing a system that I could auto-promote stacked storage with a copy onto the heap if it overflowed. And that was not fun, and it was not easy, and I'm sure it still has bugs in it to this day. But Go made that trivial to do, right? And so when I say, I hadn't seen it before, it's because if you know how to use those types of things in Go, the Stop the World garbage collector, which doesn't exist today. It's very sophisticated today. The team has done amazing things. But back in the 052 days, it almost, looked like a just stop the world, mark and sweep type of deal. And so this is kind of what we were seeing, and you can kind of see there's some bumps, and you kind of pop up to 40, and some of the lines are flat, and some of them aren't. And when you see them staggered, I don't know if we mentioned it, but the general RTT between any type of servers within the different cloud providers, about 3 to 5 milliseconds. And so remember with NATS, one of the things that's interesting and I think powerful is it's location independent. We are truly nomadic secure applications, meaning if I connect to a server and then I have to one hop to the server that has the stream leader, you're going to see 5 milliseconds, 3 to 5 milliseconds more on those. And that's why you see that staggered line. And so that we expected, but we didn't expect is some of those bumps down there. However, once we determined that the memory system was it, and we knew it, and again, we had never seen it before, we were lucky because, the Go ecosystem has grown and expanded so fast, and the Go team at Google are really amazing. They have something for this. They have sync pools, and sync pools are very, very intelligent around synchronizing both what looks like on a global scale, but what they're doing underneath the covers is kind of having little per thread context versions of the blocking mechanisms. And so they're very efficient at doing exactly what we needed to do. And so everything that we were allocating, malloking, the old school, we switched over to sync pools. And so that way we wouldn't ever hit a situation where something happened with whether the garbage collectors were running and we just needed to, malloc. and alloc a couple bytes, but it would give us like a 6, 7, 10 millisecond kind of hiccup. These all disappeared with sync pools. And so now functions have all their IPQ with dedicated locks, atomics, and all of the allocations are on sync pools. And so to go back, we determined that it's an internal subscription that can be tainted with potential IO. It uses sync pools for allocation, and it uses atomics and dedicated locks for internal IPQ to kind of kick out of the head of line processing for a route to get processed. And so the final results, we saw really, really good results, in my opinion. We reached our goal-ish, we'll show you in a second. Some of them were like 21, 22, but actually I think we're doing even better today. However, not all was perfect. Again, the system can react poorly in certain setups. And what I mean by that is the system is automatically trying to balance out peer allocation. So if I create a stream and I pick, let's say, these 3 servers, and I create another stream or someone else creates another stream, we're not going to overlay them on the exact same peer set, right? So we already are doing that. And peer selection is static, but again, you can change it. It's configurable, and you can change it after the fact. But where client connections come in and where leaders, remember we're running consensus algorithms, show up is not necessarily static. It's very, very dynamic, but it can get clumpy. And so you can see clumps of connections or clumps of asset leaders, either for streams or consumers if they're also running HA. And again, we still had that large interior delete problem for our energy snapshots. But these were the results. And like I said, you still see a little bit of a wave, which again, we're watching. You can see the step functions in between some of them. And again, that comes from if I connected to a different server than what the leader is. And in this topology, because it's a full mesh one hop, you're only going to make one hop. So it'll be a 3 to 5 millisecond tax to get kind of over there. And then, of course, we have to do the NRG thing, right? Which is we have to say, okay, the leader says, I'm good. I put it into the kernel, but I need someone else to tell me that they did it as well, right? So you can start doing the math and figure out where that 20 comes from with a little bit of wiggle room, right, in the straight math. But we were really happy with it. Again, we love working with this customer. They're really doing some pretty forward-looking things in the financial services over in Europe. Now, this is the P95, and again, it looks actually worse, but it's because of the scale of the graph. If you actually look at the numbers, most of them are sub 14 milliseconds, and if you look at the wobbles are actually only about 2 or 3 milliseconds, which is okay for what we were trying to do there. So if you spread these graphs out, they would pretty much look like near flat lines, which is awesome. And so we still had next steps. Again, peer selection can be modified afterwards, but it's kind of thought of as a static type thing. In JetStream, you can, again, based on those tags, select placements, select peer selections, and you can actually use that to upgrade a stream and change its placement selection. And in NATS JetStream, you can actually do that while the stream is in use. It's kind of like changing the engine out of an airplane while it's flying. And so you can actually tell a stream, hey, I know you're placed over in AWS. I want you over in GCP, or I want you in Azure. Conversely, if your topology is set up and it's global, it's worldwide, you can say, oh, I want you to move from Europe to Asia Pac, right? And go from Google in EU West to Azure, right, in Singapore, let's say. And you can still publish messages to it. And again, JetStream allows you to create digital twins. We call them mirrors. And also you can create what we call sources, which allow you to mux. I can have one stream collect from a whole bunch of other streams. Think about edge locations. And then demux, you can deconstruct it on the other side. We needed to balance connections, and it's possible today, but it's manual. Meaning if you have a system, you can actually go ahead and say, hey, you move some of those connections somewhere else. And in NATS, the other thing that I didn't like outside of the location dependence is the dependency on DNS. And so NATS is not dependent on DNS. So as soon as it connects to any server, it understands all of the dynamics of a cluster, and it's kept in sync all the time. And so it always knows if I get disconnected where I can try to reconnect. And so in Synadia's global system, I really thought this might be an issue, especially as we did rolling updates of servers. But a lot of those those connections are more transient. So when they reconnect, they just auto kind of balance themselves out. But we need to fix it. We need to make it better, and we are. We're going to automate that. So you can imagine, a tool which we have our NATS CLI and say, rebalance connections based on some strategy and take an hour to do it. Also, each JetStream asset leader, again, HA, running the NATS Raft consensus algorithm, they are also dynamic, but they can also clump. So all of a sudden you can see a server that, let's say we have 10 streams in your system and all of the leaders are on the same server. But again, it's something that's dynamic. You can just simply send it a command saying, please step down. And within the design that we did, that's a cooperative transfer. So it's very, very fast. Now, it doesn't violate any of the Raft protocol consensus things, but essentially the leader picks the next best leader and essentially passes the baton, and that allows that peer to immediately go and collect a vote. And everyone says, yep, that's all good. And so you can step these down, but again, it might be nice, and we're going to be doing this, again, the NAT CLI saying balance the HA asset leaders for these streams based on this criteria, which could be just, where they are, or least loaded, whatever those things are, and take an hour to do it, right? Don't try to blitz it and do it all at once. And again, we need to automate that. Two things that we learned even prior to the engagement with this customer was that we needed multipath routing, and NATS V210 has multipath routing with both muxed connections and also pinned connections. So you can actually pin a route specifically to only one individual account. And there's a system account that runs all the background communications between the servers and things like that. That's automatically pinned, but you can actually take additional user-created accounts and pin them as well. In addition, we do dynamic asymmetric aware compression, real-time non-degrading, which is pretty slick. And that's from our friends over at Min.io as well. They do a S2 compressor that's really, really neat. It's awesome. And then, of course, we redesigned the energy logic. And since I was the one that did the bad version, I felt it was important for me to fix it. So it's a modified, very high-speed AVL tree now with also run length encodings in between blocks, essentially. If you remember, I said the Swiss cheese pattern, so that's the AVL. We'll take that on in chunks, and then I said the lagger pattern 1, and then there's a million. That's just a simple run length encoded encoding now on the wire. So no rocket science there either, but it makes a huge, huge difference, which is really, really awesome. And by the time you see this, NATS V210 will be released. If you want to get more information, love to talk to anyone and everyone, please reach out. And with that, thank you so much for the time. Thank you for inviting me to present at P99. Again, this was my first time, and I hope that you'll reach out and say hi.